Welcome to the notes for H5-2, graphing inverses. So our objective here today is going to be to recognize relationships between graphs of functions and their inverses in terms of their points, domain, and range, and symmetry. So there's a little warm up here, just practicing what we did in the previous lesson, H5-1. I just want you to look at this function here that you've got. G of x is equal to 3/4 times the quantity of x minus 1 cubed plus 6. And I want you to come up with the inverse equation for that. Remember, there was two methods you could use. You could either list the order of operations or the steps, and then list out the steps backwards. Or your other option there was to switch x and y and then solve it for y. It doesn't matter either way you do it there. If you want to pause the video and try that there, I'll write down the answer here for you. Okay, the answer you should have gotten, the inverse of function g, should look something like this. Now there are a couple variations on this because depending on the way you simplified there or the way you dealt with the fraction, but you should end up with the cube root of 4/3 times the quantity of x minus 6, and then afterward there, outside of the cube root there, you should have a plus 1. Now I've seen people also give me answers that look like this, where I've had, x minus 6 over 3/4, right, and then plus 1 on the outside. That is equivalent there. We try not to leave fractions in fractions, but yes, if you got that, that is also the same thing. We just try not to leave this fraction in here. When you divide by a fraction, remember you can multiply by the reciprocal, just like we did in that top answer. All right, let's move in here now to looking at our inverse graphs. The directions here state, make a careful graph of each inverse equation. Look for a way to make the graph without finding the inverse equation first. Then make statements about the relationship between the coordinates of a function and of its inverse. All right, so this first example here, we've got the function y equals 1/2 x plus 3. They're not allowing us to do it by finding the inverse equation, so they want us to do this by using the graph. So the first thing you would do here in this situation is we could take it here, and I'm going to list out some points that I see on the graph. So the first one I see here is the point -6, 0. And then it looks like we've got the point -4, 1. Looks like we've got a 0, 3. Looks like we've got a 2, 4. And then probably it looks like maybe an 8, 7 up here. Now remember, our inverse graphs, right? We're taking our original inputs there will become the outputs of our inverse function there. And then our original outputs will actually be our inputs for the inverse. So what's that mean here? We're just going to switch x and y. Do you remember when we did that solving the equations in the previous lesson? Okay, now we're just going to switch x and y because all of the points that we have, we can just switch them to make it 0, -6. If -6, 0 is on the original, that means 0, -6 is on the inverse. And the same thing with the rest of the points. So you can go ahead there and just record all of those points. 1, -4, 3, 0, 4, 2, and 7, 8. And then I encourage you now here, you may want to take a moment here and plot them on the graph. Be careful when you do this though, because if you plot a point in the wrong spot, it throws everything off. So we should have a point at 0, -6, a point at 1, -4, a point at 3, 0, 4, 2, and then I have 7, 8. And if we connect them here, you'll see this is our inverse graph. All right, we're going to move on to the next one here. And, when we're done with all three of them here, we'll kind of look at some of the relationships and things. So, second one here, it looks like we have a parabola. We have the equation y is equal to 3 times the quantity of x plus 2 squared minus 6. And again, let's take this here and let's write out our points that we see from our original graph. So it looks like here we've got a negative 4, 6. I'm going to mark this one, even though it's not even like on there, but that looks like it's about negative 3.5, 0. That's important there when we're looking at, where graphs are located. We want to make sure we can represent the x and y intercepts. And then the one after that, right down here, looks like it's negative 3, negative 3. We've got this one down here, the vertex, negative 2, negative 6. It crosses, looks like it's close to negative 1/2, so I'm just going to throw a negative 1/2, 0. And then it looks like we have one more point up here at 0, 6. So with that being said here, remember, our inverse graph then is going to contain all the points here where we're going to switch the x's and y's. So our inverse graph should contain the points 6, negative 4, 0, negative 3.5, negative 3, negative 3, negative 6, negative 2, 0, negative 1/2, and then 6, 0. And now take a moment here to plot these ones on the coordinate plane as well. Now, I should have mentioned this before, but it's really important here when you're listing out your points, especially your original points over here, you want to follow your graph. Notice here I started with the negative 4, 6, and then I kind of just followed my graph and then listed the ones that I saw here in order. Why is that important? Well, that's going to help us here because now I know what needs to be connected when I am redrawing my graph here. I'm going to do it in the exact same order that I had written them down. So I start with my 6, negative 4, and then I'm going to go to my 0, negative 3.5, my negative 3, negative 3. I'm going to go here to what appears to be like the vertex at negative 6, negative 2. And then we're going to start coming back the other way there. 0, negative 1/2, and then 6, 0. And you see here that we have graphed the inverse. Okay, so while our original was a parabola that was opening up, this was a parabola that was on its side. Okay, so just take notice of that there, and we'll talk about it a little bit more here in just a moment. And this one, I wanted to cut down the time on this one. I should have had the points written out already, but I'm going to pause the video, look up the points. There's quite a few points on this one, but I want to really encourage you, maybe start with the one that's down here, right? And then just list the points as you come to them as you follow this graph. Okay, so follow the graph to list those points. Don't just start randomly picking off points at the top and writing them down. Follow the graph. So I'll write down the points here, and you can check to see if you get the same things. So the one I have way down there should have been negative 5, negative 8. And then we had a point at negative 4, 0, negative 3, 4, negative 2, 5, negative 1, 4, 0, 2, 1, 0, 2, negative 1, 3, 0, and 4, 4. Table wasn't big enough there because we listed so many. So then go ahead there and, take your points and flip-flop the x and y to come up with your inverse points. So you'd have a negative 8, negative 5, a 0, negative 4, 4, negative 3, 5, negative 2, 4, negative 1, 2, 0, 0, 1, negative 1, 2, 0, 3, and 4, 4. There we go. So then take that now and go ahead there and plot those points on your graph. After you plotted them all, go ahead and connect them. It should make a shape that looks like this. All right, now, the next part here is going to ask us to start analyzing the graphs a little bit here. So when you look at the graph of a function and its inverse, you can see a symmetrical relationship between the two graphs demonstrated by a line of symmetry. So letter A says, draw the line of symmetry for each pair of graphs in each of the 3 previous slides. All right, so let's go back here. We'll start with the very first one. When I'm looking for symmetry between the two graphs, what I end up seeing here is there could be a line of symmetry that runs right up through here, just like that. And you can kind of see the reflection of the graphs across that red line that I put in the middle. Let's look at the second one. Okay, these ones have some sort of symmetry as well. And again, I can take it and I can draw this line that runs right up here diagonally. And you can kind of see here that I do have symmetry across that line, or it looks like a reflection. And then the same thing holds true for this last one here. If I run this diagonal straight up through, notice both graphs will intersect there on that line as it's crossing it there. So all 3 of them have that same line of symmetry. So what does that mean? Well, it says here to find the equations of the line of symmetry for each graph. Well, I think we already found it. This diagonal line here, notice, let's go to one that's a little bit cleaner. Notice this line crosses at 0, so the y-intercept is at 0. And then it looks like it's just taking this and it's going to rise 1, run 1, rise 1, run 1, rise 1, run 1. So the slope of it is 1. So when we take our slope of 1 and our y-intercept of 0 and we put it together, what we should end up with here is the equation y is equal to x. Y equals x is going to be our line of symmetry for all of our inverse functions. Now, part C asks us, why do you think these lines make sense as the line of symmetry between the graphs of a function and its inverse relation? Well, remember our original graph, right? Our original graph, we had our inputs on there became the outputs of our inverse graph. So our original graph's inputs, which were like our x coordinates, became our outputs, which are like our y values, of the inverse graph. And vice versa, right? We could say that there to keep it a little shorter. That means that, if I had an x and a y on one function there, it's like these are going to be switched when I go to my inverse, right? So if I had a point here on the one that was like 3, let's say 4, on my inverse function here, I know that I'm going to have the point 4, 3 because my original input became my new output, which is my y value, and then this y value became my x value for my other function there. So my x's and my y's end up equaling each other between the two functions. So we've got a couple quick other kinds of examples here I want you to see. This one says, the line of symmetry you identified in the previous slides can be used to help graph the inverse of a function without creating a table. So we're going to graph this function. F of x is equal to the square root of x plus 5 minus 1. Okay, our locator point should be at -5, -1. We'll put that there. And this just has standard growth for a square root function. So we'll go right 1 up the square root of 1. We'll go to the right 4 up the square root of 4, which is 2. We'll go to the right 9 and then up the square root of 9, which is 3. And we'll go to the right 16 and then up the square root of 16, which is going to be 4. So here is that square root function. Now, if we take it and we draw in our line of symmetry where y is equal to x, we can use this line to help us graph the inverse. So here's what we have to remember. Okay, so, what happens to x in our original, right, happens to y in our inverse. So if I start on my line of symmetry here, and let's just say here I start right here. This is the point -1, -1, and I look at this distance as I go back to this point right here, right? It looks like here I'm counting backwards. Let's see, that's 1, 2, 3, 4, right? So I went backwards 4, or down 4 with my x's, right? Well, if I went down 4 on my x, that means that I would have to go down 4 on my y on the inverse, right? So if I go down 1, 2, 3, 4, I should have a point right there for my inverse graph. So I'll put that one right there. Well, if we look at this point that I started with here, this was the point -5, -1. Down here, this is the point -1, -5. So that definitely makes sense. Okay, so let's look here at another point that we can see. If I start on my line of symmetry and I go back this way, I'm going to go back till I get to this point here. And it looks like here I've gone back, 1, 2, 3, 4. Okay, so if I went back 4 again, I'm going to go down 4 units here. I'm going to go down 1, 2, 3, 4, and I should have a point right there. And we can continue to do that there, as far as, as long as you want. You can say, all right, well, I got this point right here, so let's go back, 1, 2. So that means we have to decrease our y by 2, 1, 2, and there should be a point right there. Now, when you go forward here, and I don't want to get too much writing on the graph so you can't see what you're doing, but let's look at this point here. If I go forward, 1, 2, that means my x is increased by 2, which means my y's have to increase by 2 on my inverse graph, which would put me right there. So why are we doing all this? Well, if we start to connect it, you can start to see here that symmetry. So I'm going to connect these points that I've been drawing here, right? And you'll see here it's going to go up. It's going to hit there, and then we probably would have one more point. This one, if you look at this distance from the line of symmetry all the way to the end here, how many points is that? Well, that's 1, 2, 3, 4, 5, 6, 7, 8. So that means we need to count up 1, 2, 3, 4, 5, 6, 7, 8. So that is where our last point would be, and I'll take it here and try to emphasize that. Now for you, you don't have to draw out all those little hoppy things like I did there on my graph. It's just so you could see what was going on. But you see the symmetry there between the two graphs. Now, something that I do need to talk about, and if this doesn't make sense to you as you're watching through the video, I'd love for you to ask me in class about it here. But let's talk about finding the inverse equation of this function here, right? This is a square root function. And we can see its graph already. Our graph was on here. I'm going to try to highlight that in red here so it stands out. This was our original square root function that we're dealing with. Okay, we know what that shape looks like. We've graphed a lot of those this year. Let's do this now. Let's find the inverse of this function. And you're going to do it like you did yesterday. You're going to take it and you're going to find the inverse by flip-flopping the x and the y. And now solving for y. So we'll add 1 across. We've got x plus 1 is equal to the square root of y plus 5. And then it looks like we have to square both sides. And we now have the quantity of x plus 1 squared is equal to y plus 5. And then we'll subtract 5. So now we've got the quantity of x plus 1 squared minus 5 is equal to y. What shape is this? Right, what shape is that going to be? And if I take this now and I actually even go through, let's do this one on, let's graph this on a calculator here. So let's go in, oops, wrong one. Let's go find a calculator. Here's my handy dandy graphing calculator there. And I'm going to clear these out, what I had in there. And it looks like the first thing here I want to graph is that original function. I have second square root. We've got our x plus 5. Right, and then we had minus 1 outside, right? So we look at that graph. Here's that square root curve, so you can see it. And remember, our inverse for this here is going to end up being a reflection across this line y equals x. Let's go ahead and just graph that, right? So it's going to be a reflection across this green line that you see here. So we just came up with the equation in our notes here. We just said this equation here, the quantity of x plus 1 squared minus 5 would be the inverse. But when we go in here and we graph that, we have the quantity of x plus 1 squared minus 5. Okay, when we graph that there, oh, we get a full parabola, right? You see where my cursor's at here, like I've got my full parabola on here. Okay, but there's a problem there, right? Because the full parabola isn't the reflection. You can see where the reflection is, right? I could start here and I could go up this way, and this is a reflection of that yellow function there, right? That you see on here, this side. But where's the other half? If you notice here, this parabola is not all the inverse. Only the right half of this parabola is the inverse. So we're going to have to do something to our equation that we just found. I asked you to find the inverse equation, but this by itself is not the inverse. Okay, or at least not all of it. So we need to be able to say that it's just the right side. It's just the right side of the parabola. Is the inverse, right? So the way we do that is by using a domain restriction. So we're going to say here our inverse for f of x would be like our inverse of f is going to equal the quantity of x plus 1 squared minus 5. But if we want to say just the right side of the graph, right? So we're going to be saying on our x-axis, we want to go from just here over all the x values from -1 over this direction, right? Or just this right side of our parabola is the inverse. So what we want to do here is we're going to say our domain for this function is going to end up being x is greater than or equal to -1. So this is the function, this is our inverse function, or the equation for it here, but we're only using these values where x is greater than or equal to -1. We do not want to worry about the second half of that graph there, right? We would have a second half of that graph that would normally come up like this, like you saw on my graphing calculator, but we're not including those. So that's where we have to throw in our domain restriction. So hopefully this hasn't lost you there, but let me know in class if you have questions. I'm going to cut the video off there instead of going into it deeper. All right. Hopefully this helps. Thanks for watching. This is H5-2.